Problem 17. A little confusing, but it actually has the same instructions as number 16 does. I'll scroll back up here. Sometimes these things will do that. That won't happen to you on an exam or anything. You know, the instructions would be with the problem. But it's still the same instructions. Write an equation for the plane determined by the given conditions. Okay. The last problem gave us a normal vector to the plane and a point. This gives us 3 points. That's also another way you can still do this. And to do that is all you have to do is create 2 vectors between any of those 3 points, and then you take those 2 vectors and you cross product them to get the normal vector that you need. So I label them. Here we go. PQ vector. Calculate, Q minus P. So it'll be 0, -1, -6. PR, but I could have done QR. 0 minus 3, -3. 2 minus 1 is 1. -1 minus 3 is -4. And I didn't show all the steps for the cross product, but I've done that in several problems before. And obviously just use the cross product formula. And you'll get 10, 18, -3. Now, technically, you can use any of the 3 points as the point you put into this equation right here. So the 10, the 18, and the -3 come from that normal vector, which is the cross product. Now it looks like I chose point Q because I have x minus 3, and because of the 0, you see there's only y there, and then z minus a minus 3 is z plus 3. And then just kind of multiply that out. You can see the answers are expanded out. You multiply them out, combine the terms, and then look for the correct answer. Now remember, if you had, let's say you had a -10x here. As long as all the terms, then you could multiply by -1 and change all the terms. That would be the correct answer. In other words, in this case, the correct answer is clearly D. But let's say, because it just depends on the order you do the cross product and that sort of stuff. So let's say you would have come up with -10x minus 18y plus 3z plus 39. You'd have been looking at these answers going, I don't have any of that. Well, let's assume maybe there was another answer choice that had 39 in there. Probably gives it away that this is the only 39. But you would just multiply everything by -1, and it reverses it, all the signs, and then gives you the answer listed here for D. There we have it. Find the distance from the point to the plane. We're going to use this formula, the absolute value, because this dot product might be negative, and obviously distance has to be a positive measure. It's not direction based, it's just distance. The absolute value of PQ dot n over the magnitude of n, where n is the normal vector for the plane, and P is a point on the plane. All right. So here's the equation of our plane. And here's the P we're given, but the Q, well, this is actually a little bit different than the way this is worded in the formula. It doesn't really matter which one you call P or Q, actually. See, I have listed that P is the point on the plane, and that's not what P is in this particular problem. So don't worry too much about the P's and Q's. Just know one of them is going to be a given point, and the other is going to be a point that you get off the plane. Any point that's on that plane. So you're looking for any X, Y, Z that make that work. And notice I always like to just pick one of the intercepts. So here I zeroed out Y and Z, and makes 2x equals -4. So x is -2. So I have -2, 0, 0. Yeah, but there were lots of correct answers for that. So I'll calculate the PQ vector. And it won't matter if it's PQ or QP. That won't matter. at all. So you calculate the between P and then between Q. So it looks like I did Q, negative 2 minus a minus 10 would be 8. 0 minus 3 would be negative 3. And 0 minus negative 3 would be positive 3. But the other way would have been fine. And then, of course, the normal vector is the coefficients of x, y, and z, 2, 11, and 10. So we dot these two together, and we end up with 13. And then we take the magnitude of this normal vector, which works out to be 4 plus 121 plus 100. This is the, okay, let me fix this typo right here. All right, I just fixed that little typo where I had 120. Fortunately, I had the result correct. Because I had the 15, that's correct, but I had 120 here instead of a 100 that you see now. So square 4 plus 121 plus 100 is the square root of 225, which is 15. So everything was correct, but I just wrote down that wrong. But it's fixed, and then you just take that 13, the absolute value, but it's already positive. So again, the answer has to be positive. So if you saw any negative answer choices up here, you would throw those out immediately. So here it is, 13 over 15. Number 19. Find the parametric equations for the line that's tangent to R at a given point. So tangent means we're going to need the derivative. That's going to give us our tangent vector at the point. So derivative of 2t squared minus 3t will be 4t minus 3. T plus 7 will be 1, and then k, the derivative of k will just be 0. So r prime of 2, put 2 in there, 8 minus 3 is 5, that's just a 1. So it's the vector 5, 1, 0. And now, so that 5, 1, 0, those are basically your A, B, and C in the parametric forms of the line. Now we essentially, even though I label this as a vector, it really is a point. It's the point when you put in 2 there. You plug 2 into here, you're going to get 2, 9, 1. So we have 2, 9, and 1, and then the r prime, that's the direction numbers for the vector, 5, 1, 0. So it's 2 plus 5t, y equals, x equals that, y equals 9 plus t, and z equals just 1. I put 1 plus 0t, but obviously it's just 1. So it's going to look like this answer right here, answer A. Number 20, integral. The integral of a vector-valued function is always a vector. So we'll just do the 3 individual components separately. That's fine. It looks like I kind of did them as sort of, well, you know, concurrently all the same time, since I'm still using the 0 and 3, but you could easily split them up if you wanted to. Now the first one is technically U substitution. I didn't write out the formality, but U equals 1 plus T, and I didn't change it. That's why I didn't want to do, usually I change the limits of integration for those, but I did not here. 1 plus T, so the derivative of 1 plus T is 1, so there's no effect. So negative 1/2, you add 1 to that, it's going to be 1/2, and then you divide by 1/2, just using the basic power rule. But I just wanted to mention, though, that there's no effect because 1 plus t has a derivative of 1. So we'll leave that alone for a minute. Okay, the next one's a no-brainer, t cubed. Let's come to the last one. I didn't show the work here. This integral would just be substitution. Now this one, though, the derivative of the inside is 2t. So I would have had to adjust by dividing by 2. So 10 just sits there. So there's the divide by 2 coming from the derivative of the inside. And then you do the power rule again. So you bring that t squared up from the bottom to the top. You get, makes that t the negative 2. And then do the power rule. T Negative 2 plus 1 over negative 2 plus 1. So you have negative 1, 10 over 2 is 5. So it gives you negative 5 there. So at that point, we have the antiderivative. We just plug in the 3. And it looks like I did the 3 and the 0, all at the same time. I didn't do 3 for all this and write a new line for 0. I think it just makes more sense to do it this way. So if you plug 3 in here, you're going to end up with 8 times 2, because that 1/2 flips over and makes it 8. You put 0 in here, you have 8 times 1. So there's the value for the I component. 16 minus 8 will be 8i. For the t cubed, looks like I made it just plus a negative. So instead of saying, but it would have been the same answer. But it's the negative, so I left it plus as a negative, so 3 makes that 3 cubed is 27, so negative 27 and then 0, so it makes it negative 27j. And I come over here and I put in 3. I get 10 to the negative 1, which is negative 1 over 10, which with the negative 1 makes it 1 over 10. Let's see. Yeah, negative 1 over 10, and the 10s would cancel, and it makes it negative 1/2. Then you put 0 in here, that just becomes negative 1. You have 5 times negative 1, or divided by negative 1, makes it negative 5. So negative 1/2 plus 5 is 9/2. So you have the vector 8i minus 27j plus 9/2 k. That will be answer C. Number 21, velocity vector. Okay, velocity is just the derivative of the position function. So at 4, it's going to be a velocity, it's going to be a vector. Velocity and acceleration of vector valued functions are vectors. Speed is a scalar. Speed is the magnitude of velocity. Alright, this one's pretty easy. The derivative then will be 4t plus 3. Second term will be negative 15t squared. And then 2 minus t squared will be negative 2t. And let's just plug 4 in there. 4 times 4 plus 3 is 19. And then plug in 4, negative 15t. So negative 15 times 16 is negative 240. And then 2 minus t squared. Oh, negative 2t, excuse me, I'm sorry, negative 2t. Put in 4 makes that negative 8. So there you have 19, negative 240, negative 8. All right, let's take a look at number 22. Find the position vector at time t. A particle time, find the indicated vector at time t. So this one's not plugging in an actual t, though. It's just generic in terms of t. There's no numerical value. So acceleration means second derivative. So it's cos 4t, 5 sine of t. So the first one, you got to be careful with the chain rule. Of course, the derivative of cosine is negative sine, but chain rule says we have to take the derivative of the 4t also, which makes it negative 4 sine of 4t. The derivative of 5 sine of t will be 5 cos of t. And now it takes the next derivative. So the derivative of sine is cosine, but the negative just stays there. Brings in another 4 from that derivative. So it makes it then negative 16 cos 4t for the first component. And then derivative of 5 cos t will be negative 5 sine t. So there we have the acceleration vector as a function of t, and it will be answer A. Number 23, projectile motion problems. Using I won't copy and paste. I don't have much room there. But I already had this file ready, so let's see. Oh. Where are they? Oh, here they are. So that way, let you look at these for a minute if you need to see them. Okay, and I'll go back to the problem now. So we're going to need to know what muzzle, initial speed, initial velocity basically. We're looking for V0. We're going to fire at 14,000 meters at an angle of 9 degrees to the horizontal. And there it's giving the gravitational. I had 9.8 on that sheet. This one had 9.81. It's not going to make enough of a difference, really. So to go 14,000 meters at only 9 degrees elevation, it's going to have some pretty powerful initial speed there to go that far. You can only defy gravity for so long. So the y of t equation will be v0 sine 9t minus 1/2 9.81 t squared. Now what we're going to do, and we have we have the x equation, which x of t equals v0 cosine of 9 degrees t. So what we effectively have with the x and the y here, we have two equations in terms with two unknowns, v0 and t. So we can substitute. So we take this equation, we factor out a t, and then I didn't actually show it, but I ditched. It would have produced, one of the solutions would have been t equals 0, but obviously we're not looking for the t equals 0 solution. We're looking for the time it's going to get back to the ground. So we set this inside part equal to 0 also. Yes, we don't care about the initial time. So t will equal v0 sine of 9 degrees over 4.905. So if we take 14,000, we know that's how far it's going to go. That's the range. And then we have v0 equals cosine 9 degrees t. So we can take the t in terms of v0, substitute it right in here, and notice that in this equation we have up here in the top right, we only have v0s, and that's the value we're looking for. So we just solve for that v0. So you multiply the two v0s together, you're going to get v0 squared. And I sort of flopped it over a little bit, so that means the 4.905 would go to the other side with the 14,000. And then you would divide both sides by sine 9 cos 9. Make sure you're in degree mode in the calculator. There's the calculation, but you can't see I'm in degree mode, but I am. And then keep in mind that I have the square root there, right? So this is v0 squared. So you're taking the square root of all this stuff over here to the right, and you get approximately 667 meters per second. All right. I don't know what happened here. I may fix this later. I must have moved some problems around, but anyway, that's all right. Well, I'm sure that probably didn't mess with your head too much there, but I guess this should have been before. Yeah, that's not 37 through 39. It's the next two problems. Alrighty, sorry about that. Projectile from the ground at 26 degrees. Initial speed of 48 meters per second. How far away from the launch point does the projectile hit the ground? So let's look at our y equation. Be 48 sine of 26t minus 4.905 t squared, and then we know, because the time it hits the ground, the y, the height, will be 0. So you set 0 equals this, and I factored out a t. Once again, the t equals 0 solution we don't want, because that's obviously the starting point. But this one, we can solve this inside part now for t. So you set that equal to 0 and solve for t. You'll get t equals 48 sine of 26 degrees divided by 4.905. You get approximately 4.29, which that's telling you, that's not the answer. That's telling you how long before it gets to the ground. Okay, well then the x, that's your distance, your range, how far does it go? So the x equation is 48 cosine of 26t, and now we just put in 4.29 for the t. That will tell us how far it will go in 4.29 seconds. So according to the results in the calculator, of course, degree mode again, it looks like it's going to be approximately 185 meters. Okay. It looks like we have one more of the projectile problems here. Projectile is fired with an initial speed of 528 meters per second with an angle of 45 degrees. What is the greatest height reached by the projectile? Here it says, okay, well, sometimes it's saying 9.8, sometimes it's saying 9.81. I'm certain that's not going to affect you choosing an answer on in a multiple choice question, whether it's 9.8 or 9.81. That's kind of interesting because I get these problems from different sources, and so whatever this book just uses 9.8. In other words, there's no harm in using 4.98. And look how far apart these answers are. It couldn't possibly make a difference. All right, it's going to reach its greatest height. If you think about it, it's taking a parabolic curve, downward parabola, and it's going to go on like this. And it's a little too flat there on top. But we're going to use the idea of the horizontal tangent line, the derivative. So it's going to reach its maximum height where you have the horizontal tangent line. That means where the derivative equals 0. Okay, so that's all we're trying to do here is figure out what time it takes for it to reach that point. And then when we know the time, we plug the time back into the y equation. So we don't really need x for anything here with this one. That'll tell you how high it actually went. So the y equation will be 528 sine of 45 degrees t minus 4.9 t squared. So the derivative will be 528 sine of 45 minus 9.8 t. I don't know why I bothered just using, I just decided to use the radical. The sine of 45 degrees is the square root of 2 over 2, but obviously you can just use decimal for that. But it's okay. That's the only thing. No harm. So you move the 9.8t over, make it positive, divide both sides by 9.8. So 264 divided by the square root of 2. 264 times the square root of 2 divided by 9.8 will be 38.1. That's the time it takes for it to get to its maximum height. And then to get the maximum height, you go back to the original equation up here and plug in 38.1, which is what I did in the calculator. So 528 sine of 45 degrees times 38.1 for t minus 4.9 times 38.1 squared gives you 7111.8 meters, roughly. There it is. Answer A. Excellent. Unit tangent vector. Basically means we have to get the tangent vector, and then we have to convert it to a unit vector. So here's our position vector. Let's get the derivative of that. So 5 plus 2t to the 7th will be 14t to the 6th. 4 plus 10t to the 7th will be 70t to the 6th. 8 plus 11t to the 7th will be 77t to the 6th. Now we need the magnitude of that. I pulled out a 7, and actually I probably could have just pulled out a t to the 6th. Anyway, yeah, I could have done that. I realize that now, but that's okay. What I did was not wrong, but could have just done that. So, but anyway, so I pulled a 7 out. I ended up with 7 square root of 25 over t squared, t to the 12th, t to the 12th. The square root of t to the 12th is t to the 6th. And square root of 225 is 15. So we have 7 times 15 times t to the 6th is 105 t to the 6th. Yes, if I'd have pulled out that t to the 6th, we'd have had 7 t to the 6th and then times 15 for the magnitude of what was left. So my unit tangent vector is going to be r prime of t, this vector right here, divided by that magnitude. So it's every term here in the r prime of t divided by 105 t to the 6th. So you see the variables are all canceling here. They didn't have to. They just do in this problem. Because we're not actually plugging a number in there. It's not like the unit tangent vector at like t equals 2 or something. That would certainly be numerical. This is just coincidental that it worked out, that all the t's canceled. So you just get rid of the t to the 6th, 14 over 105, 70 over 105, 77 over 105, and that actually, those all reduce by at least 7. The middle one reduces by 35 over 35. So we end up with answer A in standard unit vector form. Okie doke. Let's see. Wants to put this, it wants us basically, we're not finding the t in the n. It just wants us to, it's just asking us to find, because it's hard to tell because this is smashed up. But in the original version, it's not, I'm sure it's not smashed up looking like this. But we're trying to find just the AT and the AN components. There's different ways you can do those. Here's what I chose to do. I'll show you back on the formula sheet. It's probably wrong way. Oh, I saw it. You can kind of choose whatever way you want here. So here's the AT and the AN right here. Yeah, on problems when I worked out finding all of the components, to get A sub t, I would have done A dot t here. But we're not actually finding t, so we need to use that formula right there. This one you can kind of use either one of them because you will find AT to get. You can use this one if you want to. But yeah, A dot t was my go-to formula whenever I wanted to find, but here we just want AT and AN separately. So it looks like I just used a cross product formula anyway. Oh, because one reason I think I used that instead of the, usually I use this one a lot of times, this one right here, or the one on the right. But AT is kind of an algebraic form instead of a number in this case. It's still a scalar, but it's an algebraic form of a scalar. I decided it'd be easier just to use the other formula, and it probably was. All right, so here's R of t, here's R prime of t. That's easy enough. R double prime. There's the velocity, the acceleration. So for A sub t, well, I have A sub t on them. I'll just look at this one first. I just did V dot A over the magnitude of V. And V dot A, which is these two, this would be 4t right there. Everything else will be 0. and then divided by the magnitude of v, which is the square root of be 4t squared plus 4, when you square both of those. That actually simplifies a little bit, which may come in handy when we're looking at the answers here, of course, but it does because you can pull out a 2 from inside here. In other words, a square root of 4. So the 4 over 2 reduces to 2. So your a sub t is going to be 2t over square root of t squared plus 1. And that's the only one that has that answer, so I'm going to go ahead and identify this answer right now, but I'm going to show you the other one here also. So v cross a, magnitude over magnitude of v. So we already have the magnitude of v right here from over here. 2 square root of t squared plus 1. And I won't go through all the steps of the cross product of v and a right here, but a lot of zeros. And you just end up with negative 0, 0, negative 4 is your vector, which just gives you 4 when you do the magnitude. And that reduces to 2 over the square root of t squared plus 1. So there it is. There's your an component right there. So answer A was correct. Number 28, curvature. Let's see where that little formula is. Not a difficult formula to apply. I'm just going to show it to you on here. And there it is. In fact, I'll go ahead and just snip it out of here. Don't want that. So it's got a cross product in it. It's got magnitudes in it. Oh, I was wondering where it went. There it is down here. Okay. So obviously we need R prime and R double prime. So let's get those. R prime, negative 4 will be 0. 9 plus 2t, the derivative will be 2. T squared plus 6, 2t will be the derivative. So the next derivative will be 0, 0, 2. Lots of zeros. That'll make the process faster. I'm not going to go through the cross product steps here. But really, you're going to end up with 2 times 2 right here is 4. Everything else is going to have a 0 involved. So it's 4, 0, 0. The magnitude of that cross product then of this will be 4. Now we need the magnitude of r prime of t. Right here. So it'll end up being the square root of 4 plus 4t squared, which will be 2 times the square root of 1 plus t squared. Now notice there's a cube on the bottom of that. So we have to cube this. And when you cube the 2, that's going to be an 8. So that's what reduces this to 1/2. To now it's 4 over 8. And then the square root cubed will just be 1 plus t squared to the 3/2. So I guess I didn't realize the formula was further down there. That's okay. I'll still leave the typed version of it in there. So let's see. What do we have again? 1 over 2. Oh, it kind of fooled me for a second. I was looking at B and C and I'm going, wait a minute, are those the same answer? We might have a problem here. But then I finally saw the negative in front of that. So curvature is not a negative value. So negative is automatically wrong. Because you see it's a magnitude divided by a magnitude. Those are both going to be positive quantities. So negative is nonsense for curvature. Number 29, arc length. And once you get the integral set up, you can use the numerical integration in your calculator to do it. Basically, it's the integral of the magnitude of r prime. So the derivative will be, first term will be 6t squared, second one 6t squared, the last one 3 minus t cubed is negative 3t squared. And we take the magnitude of that. So it's 36t to the fourth, 36t to the fourth, 9t to the fourth. Add those up, you get 81t to the fourth. Square root of that will be 9t squared. So it's an easy, of course, easy integral to do this one by hand. You could still use the numerical thing. So we're just integrating from negative 1 to 2 of 9t squared. So it's going to be 3t cubed. And from 2 and negative 1, 3t cubed with 2 will be 24 minus a minus 3 makes it 27. All right, so that one was pretty easy. $30. Same thing. So r prime is going to be negative 4 sine of t will be the derivative of 4 cos t. 4 sine of t has a derivative of 4 cos t. And then 7t has a derivative of 7. So the magnitude of this is going to be the square root. It'll be 16 sine squared plus 16 cos squared plus 49 under the square root. Now, this problem, if you don't catch what I'm about to say here, when you're looking at this problem, it can absolutely drive you nuts. So this is where you've got to recognize that 16 sine squared plus 16 cos squared is just 16, because a sine squared plus cos squared equals 1. So 16 plus 49, square root of 65. And so that makes it super easy. It looked like it's going to be hard, but now square root of 65 dt will be square root of 65t. Pi over 2, 0. Plug pi over 2 in there. So it's a square root of 65 times pi divided by 2. Answer B. Partial derivatives. Check, that was 30. Yep. 30, so this is 31. We need fx and fy. Quotient rule, I think, would work best here. So with respect to x, bottom, x plus y times the top, respect to x will be 1. Minus top times the derivative of the bottom, respect to x will be 1. So that kind of cleans up in the numerator, because you'd have x plus y minus x. So it leaves y over the bottom squared, of course, quotient rule. Over x plus y squared. The fy partial. The bottom times the derivative of the top, respect to y will be 0. So with respect to y, that'll be 0. Minus the x on top times the derivative of the bottom, respect to y, will also be 1. And then, so that one cleans up and leaves a negative x on top over x plus y squared. So that looks like that gives us answer B is the correct answer. Number 32. So it's a function of 3 variables. So let's find fx, fy, fz. This one should be pretty easy. First term, x squared y, so the derivative of that respect to x will be 2xy. Middle term has no x, so we can ignore that. And the derivative of xz squared respect to x will be z squared. And the fy, first term, derivative of y is 1, so it leaves an x squared. The middle term, the derivative of yz squared should be 2yz. So there's a mistake right here, so let me fix this. Alright, so see if I can copy this. Alright, I'll pause the video to clean that up here, and now let's go back and take a look at it. So now let's look at it again now. So x squared y respect to y will be x squared. Y squared z respect to y will be 2yz. The last term doesn't have a y. So I had that written incorrectly there. Fz, first term has no z. The second one, y squared z respect to z, will be y squared. And the last one, xz squared, will be 2xz. And then there we go. Now we should have it. And let's make sure that matches up with one of the answers here. All right, so there it is. That matches answer A. So I fixed my mistake there, and everything's good now for this problem.